First, I would like to thank the organizers for making this a nice event. Good afternoon. I will introduce the so-called Minyi Huang games in the tutorial. This is actually part 1. Tomorrow I will do part 2. This is the outline of the talk. To begin with, I will introduce some background and the motivation for the theory. Then to give you some impression, I will give several illustrative modeling examples. And after that, I will use one of them to start develop the fundamental methodologies. To finish the talk, I will mention some applications and the references. So let's check. By our understanding, what is Minyi Huang games? Informally, we can say a Minyi Huang game is a situation of a stochastic dynamic decision making where each agent interacts with the aggregate effect of the whole population. Next, they are non-cooperative. This is also a very important restriction. Otherwise, if we consider cooperation, it's possible to develop a different theory. It can be called social optimization, Minyi Huang social optimization. So here we actually have an example for Minyi Huang games. I took this picture a few years ago in Paris. Actually, it's also for a meeting on Minyi Huang games. We can have a look at the picture here. Okay, beside this senior gentleman, you can see the charging pole. Okay, the light is on. Actually, if you are careful, you can see a cable connecting to the vehicle. Okay. So they are actually using electric power to charge the battery if you park here. It's really a Minyi Huang model. Actually, a Minyi Huang game. Okay. Why? You can see actually there are a lot of vehicles parking on this street. Okay, here you can see another charging pole. Okay, the light is also on. The point is that you have so many individual vehicles. Okay, they can simultaneously charge very hard. Then you get a problem because this high demand. Okay, we have put a lot of pressure on the grid. It's not good. Okay. Actually, for many places, when the demand is high, the price of the electricity will shoot up immediately. Okay. It can happen for some deregulated markets. Okay. So this is really a game. Okay. So if this is your vehicle, actually you are playing against a lot of other vehicles. Okay. So it's important for you to thinking of a good charging schedule. Okay. If now all the other guys tend to charge hard, it will be good for me to back off a little bit. Okay. I can wait so that I can save money when charging. So this is a very nice application of Minyi Huang games in this area. Okay. Actually, now there are many big groups around the world using this kind of game framework to do charging-related optimization problems. So this is to give you some general impression of the nature of Minyi Huang games. Okay. Before we introduce the story on Minyi Huang games, let's recall what happened in the past, okay, say around 150 years. Okay. Initially, we have the color equilibrium. This is for two players. Okay. You adjust the outputs. Then there is the so-called two-person zero-sum game to start the minimax theorem. Okay. This is a matrix game. After that, we see large game. Okay. It's n-person zero-sum games. Okay. Given the development up to this point, we can imagine what can be done to generalize. Okay. Obviously, we can see two possible directions. Okay. One is to include dynamics. Okay. Indeed, this happened very quickly, okay, after John Lash, okay, just 2 years after the paper of John Lash. Okay. This is actually in a markov decision process framework, okay, to handle dynamics. Also, there is the so-called differential game for continuous time. This is motivated by military applications. Okay, you can think of two fighting planes. Okay, one is escaping, the other is chasing. Okay, so you have zero-sum game, okay, for the continuous time case. Okay. Also, we can consider large population in the game. Okay. Indeed, this happened very early, already more than 60 years. Okay. So this is not new. So if we do both of them simultaneously, okay, then we can get some trouble. Okay. This is the so-called curse of dimensionality. Without thinking about time, okay, we consider 50 players, each having two states, two actions. Okay. You can see we need such a huge system configuration, okay, in order to describe the game with detail. Okay. So obviously, this is a big trouble. Okay. There is no way to do that. You cannot even find the enough memory size to record this kind of information. Okay. Even if you ask for help from a data center, okay, you cannot really have this memory size. Also, we can see some early efforts, okay, to deal with large populations. Okay. Actually, we can see some literature from 1960s, okay, actually earlier than this part. Also, for non-cooperative games, and there is a nice survey by Professors Han and Son. Okay. Actually, I read this nice article when I worked on mini-field games during the early time. Okay. Also, I would mention the so-called anonymous sequential games. There is a little bit conceptual difference between this theory and the mini-field games. Okay. Because for mini-field games, we start with a large but finite population, and we should keep track of everybody. Okay. So everybody has a label. Okay. We should keep track. The idea is a little bit different from traditional large games, okay, in which, for example, you can think of Ibsen large equilibrium. That means if you just ignore a small fraction of the players, okay, Ibsen fraction, it's okay. You can use that equilibrium notion. Okay. But for mini-field games, you cannot have that kind of small fraction of victims. Okay. You can imagine, say, we have a mini-field management model. for the university, we have a big, huge number of students. Yeah, somehow, you overcharged tuition fee by mistake. It's just for 1% of our students. Then you will have big trouble. Okay, so we need a different notion in order to optimize. Yeah. So here we will not use the traditional Epsilon equilibrium notion. We will use it by a different interpretation. So here I would give some motivation for developing the theory. Okay. Actually, in the past, when I went to different meetings, some people would ask why you guys thinking of such a problem. Okay. There is actually a little bit story. I started my PhD at Minyi. It's 1999. Probably some of you already know. During that time, it's quite hard to get funding in Quebec, okay, because if you know the political event and then the economy and so on. Okay. Minyi is an English institution. Sometimes it's harder to get funding. So there is a scholarship crisis after I started my PhD. After 1 year of my PhD study, I switched my topic. I changed my topic. I needed to work on something else. The point is that during that time, the .com sector was going up. Okay. The IT industry started to develop. Actually, some of you probably know during that time there was an IT giant called Lotel. Okay. It's a huge company. Also now it does not exist. It's very big. So Professor Keynes and Professor Ronald Malame got some contact from Ericsson in Montreal, the IT company, okay, the communications equipment company, to get some grant. It's like $10,000 per year, okay. Small grant, but it's enough to support a student. Plus some additional thing. Okay. So I changed my topic to work on a communication model. Okay. Actually, during that time, it's quite popular to switch for control person to communications. We actually have a lot of this kind of senior colleagues. Okay. They switched from control to communications because of better funding opportunities. So at Minyi, we had a colleague, faculty share numbers. Okay. He introduced a channel model. This is called the log-normal channel model in continuous time. It's a stochastic differential equation. The unit is dB. Okay. So in dB, you just get a linear equation. Actually, in communications engineering, there already existed a discrete time version for this model. Okay. It's kind of for autoregression model. So it's nice to have a stochastic differential equation here. It's mean reverting. So he introduced in 1999. So we took it immediately after 1 year. So we started to work on this. That is actually for a power control problem. So that is here, if we have a cellular network, with different mobile users. Okay, you can see what happens here. Each user sends its signal with a certain power, okay, to the base station. Okay, we know if you have 2 cell phones, okay, you cannot directly talk from this phone to your phone, okay, at least by the technology of that time. Okay. You must send your signal from your own device to the base station. Okay. So it's important to decide how much power you want to use. Okay. Because if the power is too weak, the base station cannot really decode your signal reliably. Okay. If it's too strong, it's also bad because it will produce too much interference to other guys. Okay. They cannot transmit. Another thing is that if your power is too strong, your battery will be dead very quickly. Okay. Probably you'll leave your home at 8, then by 12 o'clock, your phone is already dead. Okay. So it's important to do the power control smartly. So that's how we have this equation. Okay. And we can also see some upper bound for the control rate. Okay. The reason is that when you adjust the power here, you need to do it with some caution. Okay. Do not immediately increase your power. Okay. It can produce too much shock to other users. Okay. So this is the justification of the power control model. Next, we introduce the cost function, okay, to optimize in continuous time. And there is a good reason to introduce a cost term like this. Okay. So the basic idea is we want this this term, okay, to be related to the first term in this form. Okay. So roughly you want to have equality, okay, so that you can achieve a signal to interference ratio around the gamma. Okay. So that's the motivation. And also we have some interpretation from technology. Okay. So this is the first term. For the second term, we have a little bit of penalty on the control, okay? Because ideally, if you can do the job, it's best you do not adjust. Okay? Just keep the previous level. Okay? That's the best thing. Okay? So this is the motivation for us to introduce the model here. Okay? Here you already see some flavor of a game because this is only for user I. Okay. So each person has its own performance. Okay. Also, we suppose users are selfish. Okay. They care about their own performance. Okay. So this is a really a game. Now the question is how to solve this problem. Okay. For this game, actually, we did not immediately solve it at the beginning. What we do is to actually solve an optimal control problem. Okay. For the very initial work in 2002, what we did is actually to solve an optimal control problem minimize the sum of the two individual costs. Certainly, we can use a standard technique to solve this optimal control problem. Okay. Mathematically, it's a nice optimal control problem. So let's do some numerics. Okay, let's check what happens? When we have two users, okay, we know we will have a situation like this. We have the states. By our notation, we have dx1, dx2, then dp1, dp2. We have a steady space in 4D. Okay. That's how here we say we produce the grid size in 4D by discretization in an interval, a finite interval. Actually, we can generate a grid size like this. Okay. If you do a little bit of calculation, you can see this is already very big. Okay. Also, to solve this optimal control problem, actually we need to use an HJB equation. We have another dimension that is time t. Actually, we consider t from 0 to 1. Okay. We use the step size 0.1. Eventually, you can see in the product space with time and the special variable, you will get a really huge grid. In order to do the iteration for the discretized equation, actually I need to allocate a memory by this size. Okay, so it's really huge. The computation is very heavy. Okay. Actually, when I ran my algorithm using Linux, I can hear the big noise in the hard drive. Okay. Actually, I was very nervous. I was worried I could damage the computer so that I can get some criminal charge. Anyway, the computation is very heavy. Okay. But fortunately, the machine is robust enough. Okay. After several days, I can finish to get the output. Okay. So this is only for n equal to 2. Now, if we consider n big, okay, say n equal to 20, 40, actually by that time, okay, it's normal to have a population like 40 to 100 okay, in a cell. So you can see there is no way for us to extend the method here. Okay. So this motivated the development of a different approach to tackle dimensionality difficulty. Okay. Actually, after I finished my degree, I continued to work on other projects. Okay. So I did not really solve the original problem with large n. Later on, Keynes and the Aziz continued to do some nice numerical analysis. Okay. So it's for very big population, but if you use the mean field game approach, okay, numerically it's easy to handle. Okay. The computational load is modest. Okay, so given the motivation here, let's do a little bit abstraction. Okay, let's check what we can do if we want to develop a general theory to handle this kind of dynamic optimization problem with a very big population. So here is the conceptual modeling of the mean field game. Okay. It will look like this. Suppose this is myself. Okay. Agent I is myself. I have my own state process. Okay. UI is my own control input. Okay. So what I do is actually to play against the whole population. Okay. So in this case, you do not really pick out a particular individual inside. What you do is to treat a whole group. Okay. You only see the whole population. Okay. You do not really play by targeting a particular person. Okay, say you target on this person. No, it's not true. Okay, you do not do that. So in this case, there is some hope to introduce some kind of mass effect. Okay, M means mass effect to describe the behavior of the overall population. So let's check what happens here. Mathematically, here we know we have my own state and the control input. Okay. Eventually, it can be called a strategy. Okay. My own state strategy. What I'm dealing with is actually this object. And this is the empirical distribution of the states of all the other guys at time t. Okay. So essentially, this data is a measure valued process. Okay. And the objective is to work out a methodology to overcome the dimensionality difficulty. Okay, so here I will give some illustrative examples on the mean field game modeling, okay, because in the end, we always need to do it mathematically. So it matters to choose the models. For the illustration here, I will describe the discrete time LQ model, continuous time LQ model, Markov decision process model. This is actually for stochastic games. And finally, the stochastic growth model with a relative performance. Okay. Actually, in the economic and the finance literature, it's quite popular to consider relative performance.
What is LQ?
Okay, so here, yeah, I will show you. Okay. So this is the discrete time linear quadratic game. You can see we have n players. Okay. So here we have the state space model. Okay. Actually, if you wish, you can combine all the individual states together to get a big vector for the whole system. That is, you can denote xt. Indeed, if you want to have an overall description of the decision process, you need to have the whole state vector. Okay. And here we have this interesting term, okay, x super n. This is my notation. It's the coupling term. It's kind of average across the population. Okay. So you have some kind of coupling with other guys. Okay. You can also see the coefficient 1 over n. So that means say here we have this room. Okay, somehow we have a mutual interaction. If I consider myself and a particular person in audience, then the actual connection is relatively weak, okay, because it's controlled by 1/n. Okay. So you already see some kind of a mean field structure. Okay. Actually, you can compare this with the previous power control problem. Okay. So this is the control input of this player. Okay. And the WT is the white noise. Okay. To simplify the description, you can simply assume IID across all users, okay, also with respect to time. Okay. And here we can see the cost function. Okay. We do summation from 0 to infinity. Okay. So it's important for us to introduce a discount. Okay. Rho is from 0 to 1, because otherwise, without the discount, in general, you will get just infinity. Okay. It does not make sense. And in the cost structure, you already see some kind of interaction with the whole population, because now again you have this average term. Okay. You can regard this as some kind of social conformity. Okay. You want to adjust your state to keep track of the behavior of the whole population in some sense. And finally, we have the penalty in the control energy, okay, because it's quadratic. We can call it the control energy. Okay. So here for the dynamics, we have a linear equation. Okay. That's how here we put a linear. In the cost, we have this term inside. Okay. It's quadratic. Because by our notation, we know if we have the quadratic form, we can write in this way. Okay. So this is really quadratic. Also quadratic for the control energy. Okay. This is actually a standard linear quadratic game, okay, because in the dynamic game literature, in the past, we already had this kind of models. Okay. The new feature is that here we have the specific interaction through the mean field term or average term. Okay. So now I would use this as the first example. The reason is that in control theory, there is a tradition to work on linear quadratic problems. Okay. The reason is that by using this cost structure, you can get a very nice closed form solution. Okay. You can use it for optimal control problem and also for filtering problems. Okay. So there already existed a very long tradition of considering linear quadratic models. Okay. So that's why here I use this as the first example to illustrate the idea of modeling. Okay. Actually, in control theory, in around 1960, okay, Rudolf Kalman developed a very significant theory, okay, for this kind of linear quadratic problems for control and the filtering. Now we switch to continuous time. So this is essentially a continuous time counterpart of the previous example. The difference is we replace the previous difference equation by a stochastic differential equation. So here Wt is white noise, and in the continuous time case is given as a Brownian motion. For the other parts, we still have the linear structure here. Also the mean field Carleton term and the quadratic cost. Because it's continuous time, now we need to do integration from 0 to infinity. So this is the continuous time LQ modeling for the game. Here, in order for us to mathematically determine the state process, we need the stochastic integral. That is Ito's calculus. At this point, even if you have not used stochastic differential equations, it's still possible to very easily understand the solution of a stochastic differential equation. So here, for illustration, let's consider a general nonlinear stochastic differential equation. That is, we're thinking of dxt equal to fxt ut dt plus gxt ut dwt. And this is the Brownian motion. Given the stochastic differential equation with initial state x0, actually there is an easy interpretation by discretizing time. So the interpretation is we can write according to a difference equation. And for simplicity, you can consider uniform partition so that at each step, you always stay on the grid. So numerically, you can use the difference equation to simulate the stochastic differential equation. So it's not so abstract. The next example is a Markov decision process. Here we have n players. Each person has its own state and action. A is for action. Suppose we have some kind of a transition rule. The state xi has transition affected only by its own action. And we can also introduce the cost jj in this form. So here we introduce the discount factor, and the L is for the one stage cost. It depends on your own state the average state across the population than your own action. Okay. Actually, in the literature, this can be called a stochastic game, okay. As initially introduced by Shapley. Now let's check another example. Okay. This is based on a recent work. It's actually a meaningful game special issue of applied mathematics and the optimization. Consider the dynamics of n agents. Okay. Here, xti is the capital stock of the ith player. Okay. We have some initial capital stock. Here, C is the consumption rate. Okay. So essentially for this model, Ci is the control. Okay. We also have a little bit interpretation about the dynamics here. Okay. Essentially, this alpha power part is the Cobb-Douglas production function. Okay. It's a standard in stochastic growth theory for endogenous growth modeling. Here, this term is for stochastic depreciation. Okay. And also we have some standard independence assumption about the noises. Okay. And for our optimization, we take the special choice for gamma, okay, to be used below. And we have some justification. In this case, actually, all the agents have independent dynamics, okay, because you can see here everything is about the agent itself. Okay. It has nothing to do with others. Now we will get a connection of different agents. We introduce the utility function law for agent I. Okay. Here, the important term is actually U. Okay. The utility function, you can see it depends on its own consumption rate. Okay. And then another term, let's check. What's the definition here? Okay. It's actually the average. Okay. For the average here, inside, actually we added the power gamma. Okay. We do not directly use CTI itself. There is a good reason. Okay. First, we know after the power, this term has some interpretation according to utility. Okay. So this whole thing is like average utility of the population. Okay. It measures how the population is satisfied in some sense. And in this case, actually, we can write J, okay, in the detailed form, and we now have the natural interpretation. That is, it's actually a geometric mean of earned utility. You can see here we have the gamma power here. Okay. So it's kind of a utility. So here, only utility. For the second term, it's a ratio. Okay, it's called relative utility. Okay. So finally, you just make a geometric mean. Very recently, I saw some people doing similar optimization problems for portfolio optimization, also using the mean field game framework. So before we describe the fundamental ideas in mean field games, let's still try the conventional methods. Okay. Let's check, just try our lucky. Okay. We actually try example 1 prime. That is the continuous time LQ game. Okay. What we do is to build a very high dimensional model. Okay. We write the vector, and in the end, we can get the system dynamics, okay, dxt. We have very big matrix, okay, xt, and also a quite big matrix using ut, and finally we have noise. Okay. Just write the individual dynamics, okay, in the centralized form. Okay. Write a very big equation system. We know if we want to find the large equilibrium for the dynamic game, we can use dynamic programming, okay, to write a very big equation system, okay, by dynamic programming. But here we can see immediate difficulty. We need to solve a very large scale dynamic programming problem. Okay. So it's a lot of computation. There is another trouble. Each individual strategy will be a function of xt, this huge vector. Okay. This is too much information, okay, and maybe unnecessary. In many practical situations, this is not realistic. Okay. You can think of an investment problem. Okay. Actually, now some people are using mean field games to solving investment problems. Okay. If you use the traditional approach, you need to use a lot of state information. So now let's think of this. I have this number of shares. Okay. I also have a certain amount of money. I have some capital in my pocket. I can ask you how many shares you have, how much money you have in your pocket. Certainly you are not willing to tell me, or you just tell me the wrong information. Okay. So this is a serious constraint. Okay. If you demand too much information, that could be a trouble. Okay. So we want to overcome this kind of difficulty. Now let's check what can be done in order to overcome the dimensionality difficulty through mean field game theory. Here we have the fundamental diagram of mean field game theory. This is actually for the very basic part. Okay. For the basic theory, now the theory has been extended beyond this structure. Okay? But it's good to start with the diagram. Okay? Let's check what we can do in this kind of large-scale optimization problems. First, we have an n-player large game, okay, with individual states, individual strategies, individual costs. Okay. You already see 4 examples, okay, in the previous part. Okay. In order to find a useful solution, what we can do? Intuitively, there could be 2 possibilities. One is to try the blue route, okay, as done by Leslie and Leon. The basic idea is the following. Okay. Try to solve a larger scale optimization problem directly. In some sense, okay, you may make some restriction if necessary. Okay. In any case, it's to write down a very large scale equation system for the solution. Okay. So, for example, here you can get n coupled dynamic programming equations. Okay. Certainly, you cannot stop at this point. Okay. Otherwise, you will not get anything meaningful or useful. Next, what you do is to let n go to infinity, okay, and they check whether this gigantic equation system can crystallize into something really simple. Okay. Indeed, they could do this, okay, under some restriction. This is actually a very hard problem. In the end, what is obtained is actually 2 equations, basically. Okay. One is an optimal control equation. The other is an equation describing the mean field dynamics. Okay. Here we use mu-t to describe the mean field. Okay. We interpret mean field as the overall effect generated by the whole population. Okay. So normally, it's just a probability distribution. The 2 equations can take different concrete forms. Okay. For example, it can be one HGB equation plus one Fokker-Planck-Kolmogorov equation. Or it is an HGB equation plus a Minkowski-Vlasov stochastic differential equation. Here, the Minkowski-Vlasov equation is actually equivalent to a Fokker-Planck equation. So this is the blue route. Okay. You need kind of brute force, okay, to do some really hard work, eventually get a limit. Okay. It's indeed very hard. Okay. So for this reason, normally you need to have a restriction on the model itself. Okay. The model should be relatively simple so that you can move forward. Okay. Otherwise, you can get stuck too early. Here we have a different approach. Okay. It's called the red route. The basic idea is to construct a special optimal control problem of a single player. Here you have its own state, its own control. And also a mean field, mu t. Okay. This mean field is used to approximate the overall effect generated by the population. Okay. So here you have the immediate question. If we take the right route, okay, you should ask, what's the right choice of the mean field? Okay. If we get this problem, it's like a chicken egg situation. Okay. You have some kind of circular situation. Okay. In reality, nobody can offer you the mean field, the right mean field at the beginning. Okay. So it's not available. So how we can do this? The idea is you just select a general mu t. Okay. Then you proceed to solve this optimal control problem. Okay. You assume it's not given. You solve this optimal control problem. Then you can think of this is done by a large number of agents. Okay. They do this similarly. Okay. And you can then check what's the empirical state distribution of the population if they apply the strategy designed here. Then the population behavior should agree with the mean field assumed here. Okay. So the whole idea here is try to find a missing equation, okay, so that you have a well-defined procedure, okay, and you can finish the whole story. Okay. And after you finish everything, by finding that missing equation, finally what you will get is actually two equations. Okay. In some sense, it's equivalent to the first approach. Okay. Here I say, in some sense, we need to be a little bit careful. Okay. You need some condition. Okay. So this is the conceptual framework for the solution of mean field games. Okay. Now, before I describe a little bit technicality, let me mention, okay, what's the mathematical toolkit. For the analysis of mean field games, okay, we know we cannot live without stochastic optimal control. Okay. So we really need some tools in optimal control. The first is diagram programming. Okay. It's very well known by a lot of people, okay, in control or management, decision, economics, finance, and so on. Okay. There is actually another one. It's called stochastic maximum principle. Okay. It's also quite powerful. For this lecture, I will give a little bit preliminaries on continuous time diagram programming, so that we can use that to solve our problem. Okay. So let's now move away from mean field games for 5 minutes. Okay. So this is like a 5-minute course in continuous time diagram programming. Let's thinking of an optimal control problem. Okay. Here we have the state process. Okay. This is my control, ut. Here xt bar is a given function. Okay. Suppose it's a continuous function. If the time horizon is infinity, we need a little bit of restriction on the growth, okay? Because otherwise, for an infinite time horizon, when x bar grows really quickly, your cost is already equal to infinity. Okay? You don't need to optimize. Okay? It's always equal to infinity. So here we have the model. Okay? We have the controlled process, and we also have the cost function. Okay? This is actually, again, quadratic. Okay? We need to find the ut to minimize Ju. Okay? So the task is to find the u to minimize let's check how to do that. Okay. We just use Carleton programming. Okay. The idea is completely similar to Discretetime Carleton programming. Okay. Although mathematically it's a little bit more complicated, the idea is the same. We know in Discretetime Carleton programming, okay, what you do is to try to solve a family of optimal control problems according to all possible initial time and initial state. Okay. So here we precisely do the same. We know that in the original problem, we have the initial time 0. Okay. We start with 0. So now we try to solve a problem with a general initial pi, tx. Okay. So we have the variable t, variable delta x. Okay. They are used as the initial condition for the control problem. Okay. And as in discrete time Carleton programming, we define the so-called value function. Okay. If we do not have the discount, this simply means the optimal cost to go from t. The first equation is actually the optimality principle. Okay. You break the original cost into two stages. Okay. The first is the small interval from t to t plus delta. And for the second stage, okay, you actually use the new time and the new position as the arguments in the value function. Okay. And the next, what you do is actually just do a little bit Taylor expansion for the function v. Okay. You actually expand this function up to the second derivative of x. Okay. And for the original stochastic differential equation, here you can also discretize, okay, by this rule. After a little bit of work, okay, actually we can derive the partial differential equation. Okay. In the first part, we have a minimizer. Okay. Actually, once you can find the minimizer, it tells you the optimal control. Okay. So it's very neat. If t is finite, we need to add the terminal condition for the value function v. Okay. This is completely standard. So I've just added here. And finally, to solve the HJB equation, we denote v in this form, okay, as a quadratic function of the argument x. Okay. And next, we substitute this together with the derivatives into the HJB equation. Okay. And next, we compile the coefficients for the quadratic part, linear part, and the constant part. We can derive 3 ordinary differential equations. Okay. But here we only need to display 2 equations. One for this P, the second for this S. Okay. For our optimal control strategy, we do not really need this Q. Okay. It is used in calculating the optimal cost. Okay. So finally, we can solve the optimal control. Okay. You can see it's actually a linear feedback. It's very neat. Okay. And you can solve the 2 ODEs offline, okay, before you implement the control strategy. Okay. So what you need is just the state at time t. This is the linear feedback control. If t is equal to infinity, the solution can be similarly handled. Okay. The differential Riccati equation will be replaced by an algebraic Riccati equation, okay, and we can find a unique solution. Okay. In control theory, this had been developed very long ago, okay, for this kind of Riccati stuff. Okay. It's a standard. Okay, so now let's try to solve the mean field game for example 1 prime. Okay. We use the LQ model to illustrate this methodology. I hope to give some details. The reason is that the procedure here is very robust, okay, and can be applied to different models, okay, not just to LQ. Actually, now this procedure is almost like a standard one. Okay. It's used by a lot of people to solve many different problems. Okay. So let's check how to do that, okay, in order to find a solution for this mean field game. Let's recall the previous fundamental diagram. Okay. Let's go back. Along the right route, I said we need to solve a special stochastic optimal control problem by assuming that the mean field were given. Okay. There is no game, okay, just stochastic optimal control. Now, let's check how to implement that step. We know this is the original LQ mean field game. We have n players. Okay. You have the actual coupling with the population average. To follow the right route, okay, we need to introduce the optimal control problem P infinity, because this is kind of approximation. Okay. Here I use the subscript infinity. What I do here is to replace this term, okay, by xt bar, because this is a linear model, and we directly have the average of the population. Okay. So by the law of large numbers, okay, we believe it should be okay to introduce a deterministic function to approximate this part. Okay. You do the same within the cost. Now we just assume the deterministic xt bar were known. Okay. So we can solve this problem. We know in reality it's not known yet, okay, but we just suppose it was known. Okay. Then this is just a standard optimal control problem. Okay. And we just invoke the previous result. Okay. We know how to find the optimal control problem. So it is an easy job to finish step 1. Now for step 2, we need to use consistency condition to find an equation for xt bar. Okay. Why we need to do this? The reason is that in step 1, we assume it was known. Okay. In reality, it's a genuine unknown. So we need to find an equation. Okay. We know in mathematics, say when we did our middle school, sometimes we have 3 unknowns. At this moment, we just have 2 equations. Then the teacher will tell us, okay, you need to try to find another equation. When you have 3 unknowns, you should try to find 3 equations. Then you can solve it. Okay. So roughly here, the situation is very similar. Okay. We need to find a missing equation for xt bar. Okay, so this is the importance of the consistency condition. The question is how to do that. First, let's recall the previous preliminaries. Okay, we know we can solve a Riccati equation as an algebraic equation, then an ODE, okay, and finally write the best response in this form. Okay. Now we can plug in the control U height into the original dynamics, okay, and the equation of xti will be given in this form, okay, because you have already replaced this UTI by the obtained optimal control. Okay. We call this the closed loop, okay, because you already implemented the control strategy. Okay. You get the closed loop. Now let's check what's the idea to find an equation for xt bar. The idea is very simple. Okay? For the illustration, here we consider homogeneous agents. Okay? They are all symmetric. What we do is actually to rewrite the average for the states. Okay? We can then have d1/n sigma we just average the stochastic differential equations to get A minus B. Now let's check what happens if n is large. We know by the law of large numbers, if n is large, the noise will be averaged out. Okay. And intuitively, this will converge to something. Okay. Say we should converge to so we should introduce such a quantity as the limit. So if we just take this, there is another problem. Okay? You introduce yet another new unknown. That's not good. Our idea is to actually to prevent the increase of unknowns. Let's check. Okay? What should we do? Do not forget our original intention. Okay? The key thing is that when we introduce this object, okay, the purpose is to approximate this average term. Okay. So now you are doing averaging again. So basically, they should mean the same thing. Okay. That's called consistency. Okay. And we simply cite this as x bar. After that, there is no increase of unknowns. Okay. The number of unknowns is the same. The number of equations is increased by 1. So there is some hope to get a well-defined equation system to solve. Okay, right. So this is how we can impose the consistency condition, okay, so that we get this ODE. It's a new equation. It's actually just the same equation here. Okay. To summarize, now we have two equations. Okay. This is actually the one we just derived here, okay, because we have the same unknown with the coefficient g. Okay. We can write the first part of solve this part. Okay. That's how we can write this term. Okay. S is repeated from the previous page. Okay. So this is the mean field game equation system. Due to linearity and the quadratic cost, in this case, we actually get a really simple equation system. Okay. The second equation is essentially from dynamic programming, okay, from optimal control. The first equation is for the dynamics of the mean field. Okay. It's just one illustration of the diagram. Okay. You have one equation of optimal control, one equation of mean field dynamics. Okay. And now we can try to investigate the equation system. Okay. The first is question 1. Does there exist a unique solution to this equation system? Okay. Under some reasonable conditions, we can show existence and the uniqueness. Okay. The main approach is to do fixed point analysis. Okay. If it's for symmetric agents, we can use subspace decomposition of the ODE system. Okay. It's not hard. Second, how is the solution used in the n-player model? Okay. We know in the fundamental diagram, we eventually generate a very compact solution here. Okay. Just two equations. But we should not stop at this point because this is not the real world. Okay? We need to go back to reality. Okay? That's why here we need to check performance. Okay? So we need to apply the solution here to the true system. Okay? The answer here is we can use the solution to provide decentralized strategies. Okay? Indeed, for player I within the finite population, we can use the strategy here. It's very neat because it does not need the state or sample path information of other players. Okay? It's only a feedback using its own state with limited information. That's why here we say this is decentralized. Question 3. What is the performance of the set of decentralized strategies? To analyze decentralized strategy, the performance, we can introduce a strategy space. Okay? Basically, you are allowed to use state information of all the other guys. Okay? So this is called centralized strategy. Okay? Also, we want to have decentralized strategies. It's still useful to introduce this site for characterizing performance. After reasonable assumptions, we can prove a so-called epsilon-Nash equilibrium theorem. Okay? So that is, for myself, okay, even, I need a little bit of correction. It should be GI UI, U minus a height, then GI UI. So even if you try to use all centralized information, you cannot really gain too much. Okay, here we have the bound estimate. Okay. This epsilon-Nash equilibrium is different from the definition with continuum population. Okay. We cannot have a victim like 1% of the population. Okay, next, how much efficiency loss we have. Okay? In order to answer this kind of questions, we need to introduce the so-called social optimization problem. I will do it next time. Recently, in the mean field control community, people start to pay attention on the so-called efficiency issue. Question 5, heterogeneous agents. The answer is yes. We can generalize the equation a little bit, and we can do it. And we can also further generalize to more difficult models. For reasons of time, I will skip this part. Okay? I will move it to the lecture of tomorrow, but I can display the main result. Okay? So here I will briefly overview the key result of the equations. Okay? You have two nonlinear equations. One is optimal control. The other is for mean field dynamics. Okay? And there is also the independent work of Lasty and Leon. They developed their two PDEs. Okay? And finally, we can put all the PDE or PDE-SDE results into this big picture. Okay? So this is one specific situation for the fundamental diagram, okay, if we consider nonlinear diffusions. We also mention some applications of mean field games recently, and there is also some basic reference. Okay. For this talk, I only mention some papers and insert them in the lecture. Okay. They are randomly sampled. For more reference, you can check this list and the papers within. Thank you for your attention.